this is The Sky's the Limit, brief introduction to beginning calculus. So I just want to see how much of my audience knows about calculus. So how many people have heard of functions? Please raise your hand. Okay. How about limits? Okay. Derivatives, not like coin derivatives, but mathematical derivatives. Okay. And integrals? Okay. All right then. I'll start from limits. So it's best explained with sitting down and drawing a small picture. So I'll start with a line function. I know it's not perfectly straight. So this is the graph. And let's say this is a function f of x. And it's a constant function, so it's got the same value for all values of x. Yeah, this is touch as well as pen.
No, it's not. It needs to be close to the path.
And let's say, let's say the constant is 7, for no real reason. And it can be any constant, actually. It works with anything. And unless it's 3. Now, the limit as x goes to 3 of this function means all we're looking at, you're just looking at the, as x heads slowly towards 3, what does f of x approach? Like, for example, at x equals 2, it's 7, of course, because it's a constant. Then at x equals 2.5, it's still 7. And x equals 3.5, still 7. So as x approaches 3, what does f of x approach? Does anybody want to guess? Think you guess? No? Yes, it's not that correct. It will still be 7. Because it still equals 7. Because as you approach 3, it will just always be 7 because it's a constant function. So it will remain 7. So that's the basic idea of limits. There are more rigorous explanations, of course. So let's do a piecewise function. I'll explain a piecewise function because it's might be a little obscure. Okay, so a piecewise function is a function that is it's a function that is streaky. Function that this is a special slide. No, maybe it's basically it's equal to one certain function like x squared for certain values of x, like x equals to 3. And for all other values of x, it's maybe like 7x. For different values of x, this is a mathematical symbol meaning in. So the interval 0 to 1. 0. I can draw that in all other intervals, let's say. All other x. So that's basically what a piecewise function means.
Ajay,
So we
Ajay.
got a simple one.
Excuse me, Ajay.
Yeah?
Could you write out piecewise so we know the spelling?
Sure.
Yeah, you can type it too. Use the A.
Yeah,
Use
I
the A
will
and
type.
type. Yeah.
Oh, let's type. It's been a long time since I've done this. Piece. Everybody can read that, right?
Yeah.
Okay.
Thank you.
So this is what piecewise functions are. And let's draw a simple one. This will work. Yeah, I know the one. Let's say it's again constant, but except at x equals 3, right? X equals 3. So it's 7 here, it's 7 for all values of x, except when x equals 3, and it's 9, for example. So, as x approaches 3, what is this piecewise function? What is the limit as x goes to 3 of this piecewise function? A younger member of the audience want to take a guess? So who wants to guess as x equals 3? Alright, even though f of x at 3 is still 9, the limit as x approaches 3 is still 7. Still equals 7. Because as x approaches 3, f of x still approaches 7. It doesn't suddenly jump up to 9. If you had a little curve here, for some reason, then you could say that limit as x approaches 3 of f of x is 9. But it isn't here because it's just a jump up as x approaches 3. It's equivalent to 9. That's how you, that's a not very rigorous mathematical way to define limit. And of course there are several types of limits. I'm going to asymptote. Let's make it. Travails of writing with paint. Let's say this is 1 over x squared. Function y over 1 over x squared, which means as you take a value of x, like 3, you just square x, you take the reciprocal, you get 1 over 9. And as you can see here, it just seems to go up and up and up, right? There's no point where it just turns. Because as you approach 0, x squared becomes 0, or approaches 0, and y approaches 1 over 0, which is undefined. Since here x squared is always positive, we can actually say that this will be positive infinity because 1 is positive, and this must be positive, whatever the sign of this or this is. So this will approach positive infinity, even though at any point it's not at infinity. So we write that the limit as x approaches 0 of this function until y is infinity. So that's an asymptote. And you can also have asymptotes where it only approaches infinity from one side. Not imaginary, it's in square root negative 1. here it approaches infinity, here it does 6. And then in order to label what this is, we call it as 0 minus sign, because we're going from the left side of 0. Left side 0, 0. So as you approach from the left side, this function that's we have infinity. But if we approach from the right side, we get 6, because it just remains at 6 until here, where it becomes infinity, undefined. We put a plus because we're approaching from the right. Okay, so that's some basic limit stuff. Limits things. I'll talk about continuity next, because that's a very important. So a function is continuous when it's the limit of that function as approaches, let's do a negative. As this function approaches negative 5, it seems to be equal to f of x again, or g of x, because f of x is bounded. But here it jumps up. But since the limit would be here, around this point, but it's actually evaluated up there, this function is not continuous. Because the limit at that point is not equal to an actual value at that point. So write g of x not that's short.
Not continuous.
Right, and that's enough about limits. Let's do some more interesting things. Let's do a bit of derivatives. So does everybody kind of get limits now? Or are you all just nodding to please me? So let's say we have a little squiggly function. And you want to find the tangent line. That is a tangent line. And the tangent line, of course, is the only point where it's the line where it just touches that function f of x at one point only. Just that one point. At least along this neighborhood of points. And you can actually see how we can calculate that by drawing some secant lines. The secant lines they're called secant lines because they still intersect as 2 points. You can see, and the slope, let's say this is over, let's say this point over here x equals h. Let's say this is h plus delta h. Then the slope of our secant line would be f of x plus delta h. Sorry, h is h. Because that's the rise in the secant line. Because slope is rise over line, correct? So the rise of this is fh h plus delta h here, plus f minus f h. And this is all divided by the RAP, which is h plus delta h minus h, or delta h. Right. But that's not the tangent line, so why are we even considering this? Well, if you take the limit as h plus delta h approaches h, you can see that the line sort of starts to approach the tangent line, correct? So in order to find the slope of the tangent line, we can just take the limit as h plus delta h approaches 0. It's the same thing, because if delta h approaches 0, then h plus delta h approaches h. And that is the definition of the derivative. Again, the derivative is the slope of the tangent line at that point. And this is interesting because if you have a function, let's say we have a function that defines something we want to measure, like how many corn crops are produced every year, for example. Then if you want to see how quickly the corn crop load is increasing, you can just find this derivative, because it's the rate in change of the function at that point. Because, yeah, it's the rate in change of the function over the rate in change of x, so to say. And you can use this to determine that. And you can't just use this definition all the time. This definition, I'll box it up, this is very important. All the time, because it gets extremely tedious. So we have a few shortcut rules. Like if f of x equals x to the power of n for any number n, you can let it even be like x to the 3, then f prime of x, which is a symbol used to show the derivative, is equal to. Apparently, Newton invented this notation. Originally, he put a little dot up on top, but that became quickly confusing. Somebody put a period here, and then later they put an F there. People think it's a derivative sign. So we changed it to F prime. So F prime of x is 3x squared. And in general, and this applies to any number. And let's see, f of x is x is 1. And a few other rules too. Yeah, and there are also integrals. I probably don't have enough time to go into enough detail about that. Basically, it's just the area under the curve. So this is f of x. You want to find the integral, it's just this area. And that's denoted, basically denoted a, b, f, x. And there's a highly important theorem called the fundamental theorem of calculus. You can see it's very important because it's fundamental. That the derivative, if you want to take the indefinite integral, that's just the function, basic function. So if you take the derivative of this, it's equal to the original function.